Okay, so we can start. Um, say we started with impulses and momentum, where we discussed momentum. Today we will start with conservation of momentum. Okay, so what do you mean when we are talking about conservation of momentum? Okay, so we say that in order for the objects to change momentum, then it needs impulse, because the impulse is the one that is responsible for the change in momentum. Okay, so the impulse must be exerted by something outside the object. Okay, so because if you have internal forces, the one, since it comes in balance pair. So like when we discussed, we said when we were talking about Newton's third law, we said that for a forces reacting to an object, there is always an equal forces in magnitude but in opposite directions. So which means now if the object has only the internal forces, if it is only the forces within the object, if there is no external forces, then the object won't change the momentum if there is only internal forces acting towards that object. So if there is no net forces or a net impulse acting to an object, or let me say to a system, then the momentum of that object will not change. If there is no impulse acting to an object, then that object will not change. Okay, so the system where there is no external forces is called isolated or closed system. Okay, so that system where there is no net force or the net impulse force, the net impulse act on the system, then that system is called isolated or closed system. Okay, so if the system is closed, is a closed system, then no force, no impulses or external forces acting on the system, then the law of conservation, the momentum of that system is conserved, which means that the initial momentum and the final momentum of that object, they are equal, but in the opposite directions. Remember that the momentum is it's a vector. Okay, so if an object is in a closed system, then we are saying that the momentum of that system is conserved, because there will be no change in momentum. The change in momentum of that object is going to be equals to 0. Okay, so the momentum of a system, okay, when we talk about a system, if there are many forces acting in the object, we simply sum up the momentum of the individual force. Okay, so simply the summation of the momentum, depending on how many momentums are acting on that object. Okay, so when the object interacts, as I said, okay, in a closed system, then their total momentum before interaction and after interaction is equals to 0, or it's the same. So then we are saying that the system has a conserved momentum. Okay, so what we mean is, if this is an object, we say that for every object, there is a reaction force. Okay, so if I say, okay, to this, let me say if I apply a pulling force, okay, if I apply a pulling force, I am pulling an object up. Okay, so I apply that force, a pulling force. It is an external force. Then to every force there is a reaction force. So I can say this is a force. This is a force reacting to that force. So it comes in pairs. So it means that if this object, if all these forces are just internal forces, there is no external forces like friction force, air resistance, pulling force, and so forth, then the forces that are acting on this object, if you sum up those forces, the net force of that object is going to be equals to 0. Okay, so if you apply the momentum, if you say, okay, this object changed from this point to that point, okay, then the momentum, the initial momentum of this object, if this is the initial momentum and this is the final momentum, then this momentum, the initial momentum, is equals to the final momentum if that system is a closed system. Okay, so then we are saying that the forces or the momentum of that system before the interaction, okay, and after the interaction, they are equal. Okay, let's look up on this. Let's say if we have a system, I can say, let me say if we have 2 cars, for example. Okay, this is car number 1, and then we have car number 2. Let me say these cars are traveling in the same direction. Okay, then this is now when they come in direct, when the separation appears between the two. Let's say if these cars comes, when they bump each other, the collisions they interact one another, then car number 1 change the direction going in that, while car number 2 change the direction, continue in the same direction, I mean. Then if this system is a closed system, okay, then the momentum before the interaction is equals to the momentum after the interaction. Okay, so it means if I calculate the momentum after the interaction and calculate the momentum before the interaction, this momentum should be the same. Okay, so it means that if I calculate the change in momentum is going to be equals to 0 because it's happening in the closed system. Okay. So we discussed, we said a bit of a collision. Collisions is just when it comes together. Okay, so with us here with collisions, we refer to the interactions. Okay, we like the two objects or two or more objects interact together. Okay, and we are mostly, our focus is just going to focus in the closed system. So it means we are only going to look when we have a closed system, so where the momentum is conserved. So for everything that we are going to do, we are going to assume that that object interact within the closed system. Okay, so the collisions, okay, so when the two or more objects interact, okay, so then we are saying that the momentum, okay, is always conserved in all the collisions. Okay, however, the total kinetic energy may or may not be conserved. Where does it depend? It depends on the types of the collisions, which means we have so many types of the collisions, but we're only going to look at the 2 types of collisions. We are only going to look at the elastic collisions and in elastic collisions. Okay, where we're also gonna bring up a word, perfect collisions. With the elastic collisions, what is elastic collisions? Okay, the elastic collisions is defined for the collisions where the kinetic energy is conserved. So it means that when the objects collide, then they bounce off. They don't stuck to one another. They bounce off each other. Okay, so they don't come together. They bounce off. It's either it stands still or it goes in its direction or it changes directions or whatsoever. Okay, so and now here the kinetic energy is conserved. So it means that the kinetic energy before the collision and the kinetic energy after the collisions is the same. Okay, so we say that it bounces off, like let's say here we have a moving object that comes together, it interacts with an object that was at rest. Okay, so when they come together, the moving object stands